Hello everyone, welcome to another chapter of TCP/IP. It's actually the second part of routing. So if you can remember, we talked about routing protocols, RIP, RIP version 2, EIGRP and IGRP, but under those we mainly discussed about RIP protocol. Today we are going to go into the algorithms used in these protocols and to see how they actually work. Let's get on with the lecture. Couple of things that you need to understand is that a routing algorithm is like a piece of a routing protocol is like a piece of software. Example, it has a code. It should have an algorithm, that means a basic way of working. So this is what you're going to look at. So after the lesson, you will be able to compare two algorithms known as Dijkstra's algorithm and Bellman and explain the process of identifying the shortest path in a distant vector algorithm and formulate the shortest path metric using the Dijkstra's and Bellman algorithms. If these words are a little bit foreign to you, don't worry, we will discuss about these words in a bit. I want you to focus on this particular image. On the left side, you can see there are these black dots. Now these black dots are routers, and the links, the dotted lines in between these dots are indicating links. So this is a snapshot of a city. So you can see there are thousands of routers connected with one and each other, and if you want to send message from one end to another end, there are so many paths available. Now one such path I have highlighted in the red color, so you can see this clearly. The red color indicates a path from one source to a destination, and also if you think about it, if this is the source, the bottom of the line, red line, if we consider that to be source, there can be so many other paths where you can send the packet and reach the destination. In the right side, it also shows a certain network or other cabling structure, and here the colors indicate the traffic between these two or between these routers. And you can see here it's a zoom in to a certain small branch. You can see this is a massive network with thousands and thousands of endpoints. Now this is the small portion of the real picture. Now imagine this entire world. Now this is only a part of a city. Imagine entire world will have millions and billions of these devices connected to each other. So the router is the responsible device on selecting the best path available between two hosts. If you are sending a message to a remote server or a host or any form of a device, routers should be able to figure out what is the best path to send that packet. So that's the task of a routing protocol. The protocols such as RIP, EIGRP, RIP version 2, IGRP, OSPF, BGP, these protocols are doing this. So we talked about RIP. Let's see what's inside of it. Moving on, like we discussed, each router is supposed to send IP datagram. I'm going to use the word datagram here, one step closer to its destination. So how do they do that? There are two methods. One, you can configure a router to use something called the static routing. That means, otherwise known as hierarchical routing, you manually configure all these endpoints, all the destination in a router configuration. So it's the task of the network administrator to configure all of these hierarchy of containing all the destinations in a single router. If you think about it, in an ideal world, would that be enough? The second method is dynamic routing. Dynamic routing means routers communicate among themselves to determine what's the good route. So example, Internet Control Message Protocol redirect is a simple example. Now before we cover the routing protocol, we need to cover the principles of dynamic routing protocols. Now you know about couple of dynamic routing protocols. We haven't learned about the static routing, but we will do in a lab session. For now, since we talked about RIP, EIGRP, IGRP and RIP version 2, all of them are dynamic routing methods. It's not an ideal world, that's one thing that you have to understand. It's one thing that you can take the challenge of defining all the endpoints manually using a static routing. However, with the demanding changes of the network infrastructure, you're never going to keep up with the ever-changing number of destinations. Well, if you are the network administrator, if you want to select a way of routing for your network architecture, maybe for your network or a firm, first choice that you have is to determine whether you're going with static routing or dynamic routing. So like we discussed, if you take the static routing part, you have to manually define all the routes, and it doesn't change slowly over time, or only one possible route. If you have only one possible route or one destination, well, you can definitely easily configure it. However, if there are so many changes in the network, then you're not going to keep up with the changes. But this is appropriate in some circumstances. For example, if you have your own public server and there's one possible path that you have to take from that server, if you really know that that is what you want in your organization, you can set it to static routing. But there are obvious drawbacks. For example, load sharing, routers added, removed. Remember, I gave you a certain student work to do, which is to learn about load sharing or load balancing. Hope you can recall the knowledge and apply it here. And the biggest problem in the static routing is usually configured by the network administrators. Not much more to say. Reason, network administrators are humans. So there's always that human error comes into play. We might miss one letter, it will change the entire routing. Your packets will be forwarded to a different destination. The choice 2 is to go with dynamic. If you go with dynamic, routers learn by communicating with each other and they exchange more quickly. You know that you learn about RIP, which sends periodic updates. You know about EIGRP, which responds to a link cost changes or a link up and down. Imagine if you take with dynamic method, you want to go with the dynamic method, a protocol like RIP or EIGRP. Then the choice 2, if dynamic, are you going with a global routing algorithm or global routing protocol or a decentralized routing protocol? As these words are difficult for you to understand, let me give you other words which you know. Global is another name for link state, and decentralized is another name for distant vector. Now we discussed that RIP version 2, IGRP and EIGRP are distant vector routing protocols. And we also said that OSPF, ISIS, BGP, these are link state routing algorithms. So you have to select either you're going to go with global routing protocol or a decentralized routing protocol. Now in your syllabus, we need to learn about decentralized routing protocols only. That's why we talked about RIP, IGRP, EIGRP and RIP version 2. However, you need to learn how a link state algorithm or a global algorithm works. So because of this, I'm going to select one algorithm from the global routing protocols and one algorithm from the decentralized or distant vector routing protocols. Look at this example. Now these nodes here, we have U, V, W, X, Y and Z. These are routers and you can see the link between them. They are the connections between these routers, and I have given a number to indicate the cost between these links. The cost means it's the number given to indicate what sort of a traffic or maybe what sort of a delay that exists between these links. Lower the number, better the link. The faster the link, lower traffic it has. Higher the number, well, it's exact opposite. So we are looking for the best path means we are looking for the lowest cost path. So it's known as graph nodes. So these nodes are routers. Graph edges, these are physical links. Now how do you determine a good path? Now if I ask you to select the best path or a good path between U and Z, you might say that you can go from U, V, W to Z or Z. Or someone can say that no, the best path is U, X, Y and Z. Or someone can say U, W and Z. However, if you look at the numbers, you can easily figure out the best path is U, X, Y, Z. However, how do you define that? Now here we have a factor called the number, the cost. How the cost is determined? Well, each and every routing protocol uses a different metric to determine what's the best path. For example, a simple routing protocol like RIP only takes the number of routers into consideration, where the algorithm or other protocol like OSPF or BGP takes in different matters into consideration. For example, the traffic between them, the delay between them, and a couple of other factors. It's known as a composite metric. Now let's get back to our lesson with example. So what algorithm do you use in order to calculate a path between these routers? So let's move on with the link state routing protocols. Now again, we haven't talked about link state algorithms, or we haven't learned about them because they are not in your syllabus. Couple of examples for link state routing protocols are OSPF, ISIS, BGP, and they are also known as global routing protocols. And I also mentioned that they are usually complex in their behavior. Even though we are not talking about the protocols, we have to learn about the algorithms. So I'm taking one of the algorithms, most popular algorithms, which is used in link state routing protocols. Now I think you're familiar with this algorithm because you have learned for another subject. I think it's DAA subject. Well, how do you spell this? Now different people, they spell this name in different ways. I will give you a simple way. Well, try like this. Try to break this word into two. Dijkstra. So you can say it's Dijkstra's algorithm. However, there's no rule saying that you have to use the exact word, but it's easier for you to remember like that. So it's Dijkstra's algorithm. Let's see how the Dijkstra's algorithm works. Well, a link state routing protocol, most of them, they know the complete network topology. That means each and every router knows about all the other routers in the network. So this is accomplished via something called link state broadcast. They broadcast their information to others. In theory, all the nodes have the same information. And the Dijkstra's algorithm is iterative. Iterative means it runs a number of rounds. Let's say k number of iterations. After the k number of iterations, each router knows about the cost from the destinations to the every source. So this is the Dijkstra's algorithm given. It's a pseudocode. Now I have a couple of parameters here for you to go through and understand. So what happens if we go through the pseudocode, which I want you to do in detail by taking a time? You will see this algorithm. N means it's a number of nodes in your network. So it's given to the array A. and C here, it means the cost, and it takes parameters A and B, which means the link cost from one knot to another knot between A to B. And we have different parameters like dV. Now dV stands for the current value cost of a known knot, and you have a loop here which basically it's an iteration. Now let's quickly go through the algorithm and see how it works. I think these notations are not that clear to you, so I'm going to quickly apply a different color for it. Give me 1 second until I do that. Okay. I can see its initialization. We have to know the cost between two nodes to start. That means we have to know one source and a destination in order to start. And then we put into an array called n of whose the least cost paths are definitely known. That means the least cost paths are definitely known. Now this can be something like the directly connected nodes to the source. So now we can understand this algorithm looks for a source node. That means you're starting with something that you already know the cost to, and then you put it in an array where the least cost path is known, and then for all the nodes B, we are taking if the B is adjacent to A. That means if a certain node is directly connected to the A, we find the cost between that node and the known value, else the cost will be infinity. Now you're doing this again and again and again until such time where the minimum cost between two nodes are the lowest values that you can get. That means you're finding the path which has the lowest value between one source node and a destination node. So let me explain this further by going into an example. So look at this diagram right here. So we have a source node A and B, C, D, E are routers, and the cost between them is given. Alright, so let's see how the Dijkstra's algorithm works in this particular scenario. Now in order to do this for your examinations, you need to draw a table like this. So the columns are the number of nodes that you have. Make sure you indicate the source node in the first column. So in this case, the source node is given as A. So I'm going to put node A in my first column. I have node B, C, D and E. And then divide each column into two sub-columns. One side is the path and the other part is the cost. So for each node we have the path and cost. Now let's fill this. Now the first one is already filled, but I'm going to go with the first one. So node A will be the source. So from A to A there's no path because it's the cell. And the cost will be 0 because from U to U cell the cost is 0. Let's go to node B. Now in this diagram, B is directly connected to A. So we select our step is to select the directly connected nodes. So B is directly connected. You can see AB is the path which is given right here, and the cost between AB is 2. And then we go to the node C. Is node C directly connected? Yes, it is. If you missed it, there's a direct line going from A to C right here, and you can see the cost is 5, AC5. And the D is also directly connected, AD1, which is indicated here. However, node E is not directly connected to the source node A. There's no direct link between A to E in this diagram. That means at the moment we don't have a path and the cost is infinity because we can't reach from a single node. So the first step is to identify the directly connected nodes. And then you have to select the lowest cost one that we got. Now note that you can't select the starting source node out of these values. So we have AB2, AC5 and AD1, and we have one in infinity. We have to find the lowest one. So in this case, the lowest one is AD1. So we are going to select AD1 and we are going to see whether we can reach these other nodes with a lower cost value than we had earlier via AD. So let me start. What about node A? We don't take it, so we put the value path and the cost is 0. What about B? Now currently we have AB2. Now we are looking whether we can reach B via AD because that's our lowest one. Can we reach B via AD? Let's see. ADB. We can. Look at the cost. It's AD1 DB2. So the cost will become ADB3. The cost that we have at the moment is 2. So we can reach via ADB. However, the cost will be higher than what we have here. So what we are going to do is, we are not going to worry about it. We are writing the existing value because the one that we have already is lesser than the newer part that we are getting. What about AC5? Can we reach C via AD? Let's see. ADC. Yes, we can. And look at the cost. ADC, the cost is 1 and 3, that becomes 4. The current cost that we have here is AC5. So what we have is new one is ADC4. So that is a better path. So I'm going to put here ADC4. And the node D doesn't change because we are taking that node. What about E, which was previously unreachable? Now previously we couldn't reach E, that's why it said path, no path with infinity, but now you can go ADE. And the ADE path cost will be 2. Okay, so that's our second step. Now here also we have to select the lowest one, and if you look carefully, there are two lowest ones. We have AB2 and we have ADE2, but here we are going to select AB2 because it's directly connected to node A. So when you get two equal funds in Dijkstra's algorithm selects the one that is directly connected to A, or the one that has the lowest number of hops. Here we have 2 hops A and B. Here we have 2 hops A, D, 3 hops A, D and E. So we are going to go with AB2. So if you select AB2, our task is to find best path which can improve for the nodes. So node A we don't take. Node B is the one that we are at the moment, so we are going to write it exactly as it is. What about node C? Can you reach C via AB? Yes, we can reach via C via AB. It's A, B, C, but the cost will be 5. Now at the moment what we have here is 4, but what we are getting from this ABC is 5, so there's no need for us to update, so we can write the existing one as it is. Node D has been taken, so we are not going to look at it, but node E, which is ADE2, there's no way that we can get a better one because AB is also 2, AD is always it's already 2, so there's not going to be a change. So we are going to write exactly this like this. Now have you noticed that we didn't get any change? We are writing the same thing, so that can happen. So it's just a step, and we took a node to hoping that we will find a better path, but this node did not provide it. So then we go to the next one, which is ADE2, which is the lowest one. Now if we take ADE2, let's see. Now we should be able to find a better path. Node A doesn't change because that's a source node, so I'm going to write exactly as it is. Okay, and node B is already been taken, so we are not going to write that as well, but we are going to look at the node C. So we are checking whether we can reach node C via ADE. So we have ADE. Can we reach C? Yes. So the path will be ADEC, and the cost is AD1 DE1 EC1. So the cost will become 3. Now what we have here is ADC4. Now what we are getting here is ADEC4, sorry, ADEC3, which is a better path. So we can update ADC4 with ADEC3. This one we have already taken, so no change. This is the one that we are taking. So in this case we get ADEC3. Now the lowest one here is ADEC3, but if you look at it, all the rest of it is lower than that. So there's no way that you're getting a better path if you take it. But anyway, if you want, if you try it, you should see that you're getting the same thing. There's no change. So we have traveled all the knots. That means we have reached the end of our algorithm iterations. And this last one will be your answer. So this is your answer. So example, router A, if you want to reach router A via A, it's a self knot, so there's no cost. If you want to reach B, for the A, the best path is AB2. There's no other best path. If you want to reach knot Z from A, the best path that we have gotten is EDEC. So ADEC is the best path with a cost of 3. And knot D is directly connected, so we get AD1, that's the best path. E, that want to reach E, that's ADE2. So now the source node A knows what's the best path to all of these other routers. So each and every router will do this. So we have taken A as the source node. Now B will do the calculation, taking the B as a source node. C will do this, taking the C as a source node. So after you run this algorithm, each and every node of the network knows what's the best path to each other. So you can write this table after you do that. Final answer, node A, the path and the cost. You can see the same answer as we got right here. So you need to take this into this table format after you complete. Hope you have gotten a clear answer, a clear idea about how Dijkstra's algorithm works. Now, Dijkstra's algorithm is an example for a link state routing protocol. Again, to remind you what are link state, the OSPF, BGP, ISIS, these are link state algorithms. But we learn mostly about distant vector routing protocols. So in distant vector routing protocols, we have a different algorithm that is used. So in RIP, we are using a algorithm called, okay, how do you spell this? Well, it's not hard to spell, isn't it? So you don't have to make up a different name. It's simply Bellman-Ford algorithm. So Dijkstra's algorithm is for link state, Bellman-Ford algorithm is for the distant vector. I will take the same example and see how the Bellman-Ford works. Okay, so we write the first step exactly as it is. That means directly connected routers. And just like we did before, we select the lowest cost node. So we get the same answer. And in the second step, it changes. Now in Dijkstra's, when we get two similar ones, we took AB2 because it was it had lower number of hops and it was directly connected to the A source node. However, the difference in Bellman-Ford, if you get two equal ones, you're getting both of these together. So we are trying to see whether we can reach each and every node by both of these. Let's see. Now node A we are not going to take, so it's going to be no path, cost will be 0. Node B we are taking it already, so you don't have to worry about it. Node C, fine. So we have AB2, we are going to see whether we can reach node C via AB. Let's see, ABC, yes we can, and the cost is 5. And we have already ADC4. And we are going to see whether we can reach node C via ADE. Can be ADEC, yes we can, the cost is 3. So we have 2 from the two nodes. From AB node we are getting ABC5. From ADE node we are getting ADEC3. So that's the best one. So I'm going to put ADEC3. Node D has been taken. E is the one that we have now. So we are getting this answer. Now you can see the Bellman-Ford algorithm reached this conclusion one step earlier than the Dijkstra's algorithm because we took the both nodes here. So you're getting the same answer if you take this to tabular format, just like we did before. You're getting the same answer. Now let's compare the answer that you got from Dijkstra's algorithm and Bellman fault. So you can see the answers are same. However, in this particular example, we had only 5 nodes. So the answers are pretty much the same. When the number of routers are increasing, the Bellman fault will give you wrong or inefficient answers. Dijkstra's will give you better answers for when the number is high. But when you have a low number of hops, Bellman fault is faster, Dijkstra's will be a little bit slower. That's why most of the link state routing protocols are using Dijkstra's algorithm, because they are used in larger scale networks. Most of the distant vector routing protocols are using Bellman fault because they are mostly used in smaller networks. Hopefully you got a understanding about these two algorithms and these two type of protocols, and you can do an example a calculation. So I want you to follow the questions in past papers and try to do it alone by drawing that table. And there's a small homework for you. Now I have this table. I have given the protocol and the type and the algorithm used. Now we discuss about RIP, and we know the algorithm used in RIP is Bellman fault, and we have RIP version 2. It's again a distant vector routing protocol. You need to find what's the algorithm used in RIP version 2. IGRP is an interior routing distant vector protocol. Find the algorithm. EIGRP, it's an advanced distant vector routing protocol. It uses something called diffusing update algorithm. OSPF, it's a link state routing protocol. The one that we discussed is a Dijkstra's algorithm. And again, I want you to find what are the algorithms used in BGP border gateway protocol. It's a type of path vector protocol, or sometimes it's known as standardized exterior gateway distant vector protocol. So find these algorithms and just know the basics of these algorithms on how they work. You don't need to do any calculations with it or by heart anything. Just remember the algorithms. If some protocol they have multiple algorithms, remember how they work, or just try to understand how they work. So in conclusion, Dijkstra's algorithm suits medium scale network or large scale networks if they work, like OSPF. Bellman fault suits smaller scale network. Both give the same result in a smaller network, and there are other algorithms you can use. Thank you. However, I'm giving you another example here. Let me make it clear for you. So I will change the colors of it very quickly. Okay. Sorry about that, I pressed the F5 without holding the shift key. Okay, now try doing this. Your source node is source node A. Your target is to find the best path available from source node A to every other node using Dijkstra's algorithm. So post your final answer in the forum that I have given you, and you will be given marks for it. We'll see you soon with a different last chapter that we have to do on IP. Until that, stay safe.